So the second lecture in Unit 4, which is the wave nature of light, will focus on diffraction of water waves. We're going to look at water waves first, and then we'll try to extrapolate that to other types of waves. This will be section 9.3 in your textbook. So in order to study the properties of waves, one thing that we use is a ripple tank. And if you go to university and you study physics, in your waves courses, you may see one of these in one of your labs. But a ripple tank is basically it's a small little pool of water with a little source, little device that causes kind of straight wave front disruptions in the wave tank. So it'll create these really straight waves, and it makes it easier to see how other sources or other waves like light sort of reflect or refract through that surface. So there's a sheet of paper underneath there that you'll be able to see. The light will have parts where it is very bright because the light is sort of bending towards that point. It'll also have sections where it's really dark, which is where the light's sort of bending away from those points. And the water in this tank is usually about 2 centimeters. There's the light source above. It's illuminated on a screen that's below. And as you can see, the crests cause the light to, or the light converges towards the wave crests, and it diverges at the troughs. So we have these bright and dark areas. And this pattern is something that we can use to study wave sources and other sort of phenomena: dispersion, diffraction, reflection, and refraction. So back to diffraction. One other thing we can do in ripple tanks is that we can add other sort of disturbances. So after the wave has occurred, we can put in sort of blocks or other things that will affect the wave. And what we see here is sort of a block with a beveled end. And our waves are propagating as straight lines. When it hits that block, the wave starts to bend after the bevel, if it is a short wave, and if it's a longer wavelength, it starts to curve during the bevel. So I'll just read through this here just in case I missed anything. It says, if you observe straight wave fronts in a ripple tank, you can see that they travel in a straight line if the water depth is constant and no obstacles are in the way. However, if the waves pass by an edge of an obstacle or through a small opening, the waves spread out. So this spreading out, this bending, is called diffraction. And diffraction basically occurs when we have an obstacle that sort of doesn't stop the wave but causes the wave to I guess, start to bend, so it diffracts. And the amount of diffraction we see depends on both the wavelength of the wave and the size of the opening. So this question here says, what do you think will happen if the width of the slit is changed, but the wavelength is kept fixed? So we have these straight line propagation waves that are coming through this slit. If we have a very large slit, and near the center of that, we end up seeing straight line propagation, nearly straight line propagation. There's kind of curving a little bit towards the ends. But as we decrease the size of, or the width of that slit, we have more diffraction. So we end up seeing not a straight line propagation, but a more radial propagation. So that's something that's worth noting. A smaller slit causes the wave to radiate out, whereas a larger slit doesn't cause this propagation, this type of propagation. Instead, it tends to stay the same, that straight line propagation. So next question, what do you think will happen if we change the wavelength of the wave, but we keep the width of the slit fixed? So now our wavelength can be represented by the amount of wave fronts that we see. And if we end up increasing the wavelength, so we have more of these, and we keep that small fixed slit, then what we'll see is as that wavelength increases, the diffraction increases, or as the wavelength decreases, the diffraction decreases. So here's a question we'll talk through. When does diffraction become more noticeable? So if the waves are to undergo more noticeable diffraction, the wavelength must be comparable to or greater than the slit width. As such, for smaller wavelengths, such as those of visible light, you need to have you need to have extremely narrow slits to observe diffraction. So with what we're basically saying is we have that straight line propagation for a relatively large slit, and we have the diffraction for a relatively small slit. But what is relative? And it's relative to the wavelength of the wave. So if our wavelength is lambda and our slit width is w, we would end up noticing a diffraction when the lambda is greater than or equal to the slit width. So for a wave that has a very small wavelength like light, we would need to have a width that is close to that wavelength of light, which would have to be very, very small in order to observe any type of diffraction. So diffraction occurs for other waves, like sound and light. We were just looking at it for water waves, and this is usually because we study water waves because they're easy to produce. But what we see with water waves, we can extend that to other types of waves, including sound, including water. So please copy this slide down. It basically summarizes what we've been talking about already. So diffraction is the bending of a wave as it passes through an opening or an obstacle. It occurs for water, sound, and light, and all types of waves. It depends on the size of the opening and the wavelength of the wave. So as the wavelength increases, the amount of diffraction increases. As the size of the slit increases, the amount of diffraction decreases. And it's noticeable when the wavelength is greater than or equal to the width of the slit. Another way this is written is lambda over w has to be greater than or equal to 1. So on this slide it says to explain the difference between the diffractions observed. So we have the same type of wave. The width is 2 centimeters in one, and it's 0.5 centimeters in the other. The lambda for both is 0.5 centimeters. So for the first wave, because we have a lambda over w that's less than 1, we end up with a non-noticeable diffraction, except for at the edges. And in the second, because our lambda over w is 1, because it's 0.5 divided by 0.5, we have a noticeable diffraction throughout. So let's talk about sound a little bit more. So the relationship between wavelength and width of the slit and the extent of diffraction is perhaps familiar for sound waves. So you can hear sound through an open door even if you cannot see what is making the sound. And the primary reason that sound waves diffract around the corner of a door is that sound waves have long wavelengths compared to the width of the doorway. So a sound wave is usually much larger than a slightly ajar door or an ajar door. So we would have that diffraction occur around a door. Now a lower frequency sound has a longer wavelength, and that would make for our lambda over W to tend to be larger than when our lambda is a smaller number. So higher frequency sounds don't diffract as well as lower frequency sounds because those lower frequency sounds have that larger wavelength. So here's an example. If you had a marching band and they're coming to a cross street and there was a building in the way, you would tend to hear the lower frequency instruments first. So the percussion, the drums, you'd hear those first rather than the higher pitched, the flutes, the piccolos. Those would not diffract as well around obstacles. One last thing to talk about. And it says here, bats use echolocation to detect and locate their prey. Why do they use ultrasonic vibrations for echolocation rather than audible sound? So if the bats used an audible sound, it would have a very long wavelength. There would be a lot more diffraction and reflection. And that would be confusing for the bat. It would be hard for the bat to detect where something actually is. The ultrasonic vibrations have a much smaller wavelength, and that much smaller wavelength would lead to it being easier for the bats to pinpoint exactly where an insect would be that it was trying to eat, or where objects might be in the way inside of the cave that it's flying in or outside with trees.